Okay, in today's lecture, we're going to cover the second part of the section 4.1 material on subspaces. So let's get an idea of what a subspace is. So in several problems, we're going to be considering a vector space which is made up of some subset of vectors from a larger vector space. So in this case, we only need to check 3 of the 10 axioms for a vector space to see whether this subset would itself be a vector space. And the rest of the 7 of those 10 axioms are automatically satisfied because we're taking a subset of something which is already considered a vector space. So what are the 3 axioms that we need to check to see whether a subset of a vector space is itself a vector space? So here are those axioms. So here we would say that a subspace of a vector space V is some subset H of our vector space V, which has the following 3 properties or axioms. So the first property is that the 0 vector of the vector space V is in H. So it must contain the 0 vector for the space. In part B, for each vector U and V in the subset H, the sum U plus V must also be in H. So this property, again, is called closure under vector addition. So we would say H is closed under addition. And the third property is for each vector U in our subset H, and for each scalar C, the vector C times U is in H. So that is called closure under scalar multiplication. So for any scalar and any vector in our subset, the scalar multiple C times U has to still be within our subset. So any subset of a vector space that satisfies these 3 axioms is itself a vector space. So these properties will guarantee that a subset H of V is a vector space. So we refer to it as a subspace. By definition, every subspace is a vector space, and conversely, every vector space can be considered as a subspace of itself or possibly some larger space. Now, the terminology that we're going to use here is that a subspace is referred to when we are talking about at least 2 vector spaces. So if we're only interested in a single vector space, we would just call it a vector space. We'll use the term subspace if we're considering 2 or at least 2 vector spaces. And one of those spaces will be inside of the other. So one of the spaces is a subset of the other. And the phrase subspace of V is identifying the vector space V as the larger of the 2 spaces. So let's look at some examples where we're given some subset of a vector space, and we need to determine whether or not it is itself a vector space. So in our first example, we are asked to show that the set, which consists of only the 0 vector of a vector space V, is a subspace of V. So this particular subspace is referred to as the 0 subspace of a vector space, and it is denoted as the set containing only the 0 vector. So in order to show something is a subspace, we have to show that the 3 axioms in the definition all hold. So the first thing that we have to check is whether or not our subspace contains the 0 vector. So in this example, our subspace is the set consisting of only the 0 vector. So the first axiom clearly holds. We can say clearly the 0 vector is contained in the set which consists of only the 0 vector. Now, the second property that we have to check for a subspace is that it's closed under vector addition. That is, for any two vectors in our space, the sum is still in the space. Now, for the zero subspace, the only vector in that subset is the zero vector. So when we talk about taking the sum of any two vectors in our space, well, the only vectors that we can choose from are the zero vector. So the sum of the zero vector with itself, by definition, is the zero vector, because if you add the zero vector to any vector, you get back the same thing, the same vector. And clearly we've said that 0 is contained in the set containing only the zero vector. So this space is closed under vector addition. And the third property of a subspace is closure under scalar multiplication. So for any scalar c that I would choose, if I were to multiply by any vector in my subspace, which consists of only the zero vector, well, any scalar multiple of the zero vector is still the zero vector by definition, and we know that this is contained within the set which consists of only the zero vector. So it is also closed under scalar multiplication. So since all three axioms for a subspace are satisfied, we can say that this set, which consists of only the zero vector, is a subspace of the vector space V, where the zero vector was taken from. So this first example illustrates that the subset which consists of the zero vector for any vector space is a subspace, and it's referred to as the zero subspace. So let's look at some other examples. In this next one, we're told to let V equal R2, so the real plane, which is being defined with the standard addition and scalar multiplication. So we have the standard vector space R2. And in part A, we're asked to show that the line y equals x is a subspace of R2. So here let's think about how the line y equals x would be defined in terms of vectors. So the line y equals x could be thought of as the subset H of the real plane, which consists of vectors in R2, where y and x are equal to each other. So they're points xy, where both coordinates are the same real number. So the set of all points of the form, let's say t, such that t is any real number. So the set of all points where our x and y coordinate are identical. So we need to show that this is a subspace of R2, which means that we have to check our three axioms for a subspace. So the first of which, we have to show that the zero vector is contained in this set. So clearly, the zero vector for R2, which is the two-dimensional vector where both entries are 0, or we could think about this as representing the origin of the xy plane, is contained in this set H, because the xy coordinates of this point are the same. They're both 0. So it satisfies the first condition. Our second condition for a subspace is that it's closed under vector addition. So if we were to choose two vectors in the set H, let's say maybe t plus some other vector s. So these are two vectors within that subset H. When we sum those vectors using the standard addition, we would have the vector t plus s. So in this summation, the new vector that we get has components which are the same. Both components are t plus s, so this is still within the space H. It's closed under vector addition. And the third property that we have to check is closure under scalar multiplication. So for any scalar that I take, let's say some number c, if I multiply it by a vector in the set H, something of the form t, using the standard scalar multiplication for R2, I would have the vector ct. And we see that the components of this vector are identical, so this scalar multiple is still in H. So here we have shown that this subset H is a subspace of R2, the real plane. All right. Now in part B, we have a similar problem. We're supposed to show that the line y equals x plus 1 is not a subspace of R2. So let's consider how this line would be defined in terms of vectors. So here the line y equals x plus 1 could be thought of as the set H of points where the y-coordinate is 1 greater than the x-coordinate. So something of the form t for x, and if x is equal to t, well, y is x plus 1, so we would have t plus 1, such that t could be any real number. So we can define the line as this subset of the real plane. So we're supposed to show that this is not a subspace, so at least one of the three axioms fails. And in the first axiom, we're supposed to show that, or in order to be a subspace, the zero vector would have to be contained in this set. But clearly, the zero vector, or the origin, 0, 0, would not lie on this line. So here we could say clearly the zero vector, which consists of the point where both coordinates are 0, is not an element of this subset H, because if, in order for the zero vector to lie within this set, well, the first coordinate, t, would have to be equal to 0, but the second coordinate is always 1 greater than the first coordinate. There's no way that we could have the two coordinates be equal to each other. So since the zero vector is not contained in this subset, it cannot be a subspace. So the first property fails here. Now we could have also seen that some of the other properties for a subspace fail. So if we were to check the second condition, does the sum of any two vectors lie within this subspace? So let's say that we have a point of the form t plus 1, and another point on our line, say a vector of the form s plus 1. Using the standard addition, we would have the vector t plus s and t plus s plus 2. So here, the second coordinate for the sum of those vectors is 2 units greater than the first coordinate. So this would not be a point on the line. It's not closed under scalar or under vector addition. Now it's also not closed under scalar multiplication. If we have some scalar, c, and we multiply by a vector of the form t plus 1, some vector in our set H, then we would have the vector ct and ct plus c. So we see here that our second coordinate is the value of the first coordinate plus c. So if c is any scalar other than 1, we see that this scalar multiple would not lie in H. So here, the fact that these three properties are not satisfied means that the subset H is not a subspace of R2. Now we could have shown any one of these properties doesn't hold. We don't have to show that all three do not hold. As soon as we find that one property for a subspace is not satisfied, we immediately know that our set is not a subspace. In this example, we're just illustrating that all three properties did not hold. So in part C, we have a similar problem. We're supposed to show that the parabola y equals x squared is not a subspace of the real plane. So let's think about how this parabola is defined in terms of vectors. So here, the parabola would be the set H consisting of all points of the form t. So x could be any real number I want, and then the y-coordinate would have to be t squared, the square of whatever value we have for x, such that t is any real number. So we need to see, or need to show that one of our axioms of a subspace is not satisfied. So let's look at the first axiom. We want to see whether the zero vector is contained within this set. So in this example, we can see clearly the zero vector, which would be the vector 0, 0, is an element of this set H because it lies on the parabola. This parabola passes through the origin, 0, 0. So the first condition of a subspace is satisfied, so one of the second two has to fail. So let's look at condition 2. We need to show that, or check whether the space is closed under addition. So if we were to take two vectors in our space, we can see that they are not necessarily closed. So as an example, we could take the vector, let's say 1, 1, which lies within our space, and the vector -1, 1. Which also lies in this space, since the second coordinate is the square of the first. Now the sum of those two vectors would be 0, 2, which clearly does not lie in the set H because the second coordinate is not the square of the first. So it is not closed under addition, so immediately we know that it is not a subspace of R2. And just to illustrate, we could have also shown that scalar multiplication is not closed. So if we were to take, for instance, the scalar 2 times the vector 1, 1, which lies in the set H, we have the vector 2, 2, which is not an element of H, since the square of the first coordinate is not equal to the second coordinate. So as soon as we've found that one of these properties does not hold, we've established that our parabola is not a subspace of R2. So in this example, in parts A and B, we were considering lines in the plane, and we found in part B that the line y equals x plus 1 is not a subspace of R2 because it didn't contain the zero vector. Now we can show that in general, any line in R2 that does not pass through the origin is not a subspace of R2 because it wouldn't contain the zero vector. So in order for a line to be a subspace of the real plane, it must be a line through the origin. So let's consider another example, fairly similar to the last one. So here we're considering the space V equals R3 with the standard addition and scalar multiplication defined. And in part A, we're supposed to show that the plane Z equals 0 is a subspace of R3. So as with our previous example, let's think about how we could define this plane in terms of vectors. So here we can say the plane Z equals 0 is the subset H of R3 of space, such that we would be considering vectors of the form x, y, 0. So the first two elements of our vector in R3 could be anything as long as the third coordinate, which is our z-coordinate, is equal to 0. So it would be the set of all points of this form such that x and y could be any real numbers. All right. So to show that this is a subspace of R3, we have to show that it satisfies all three axioms or properties of a subspace. So the first one is that it contains the 0 vector. And here, clearly, the 0 vector of R3, which is the vector 0, 0, 0, is an element of H, since its third coordinate is 0. It does lie on this plane. Now our second condition is that it is closed under vector addition. So let's say that we take 2 points in this plane and sum them. Does it still lie in the plane? So let's suppose that we're taking the sum of 2 points, let's say x1, y1, 0, and x2, y2, 0. So these two vectors both lie in H. And we can see that their sum would be the vector x1 plus x2, y1 plus y2, and 0, which is contained in H since the third coordinate is 0 and the first two coordinates are both real numbers. So it is closed under vector addition. And the last condition that we have to check is whether it's closed under scalar multiplication. So if we take any scalar, let's call it C, and we multiply by any vector in this set H, something of the form x, y, 0, we have the vector Cx, Cy, 0, which is contained in H since the third coordinate of that vector is 0. So since all three conditions or properties of a subspace are satisfied, we can say that the plane z equals 0, which was described here as a set H, is a subspace of R3. Now in part B, we're asked to show that the plane z equals 1 is not a subspace of R3. So let's think about how this plane is defined. So here the plane z equals 1 is the set of points H in R3 of the form x, y, 1. So we can take any point in space as long as the z-coordinate is equal to 1. So x and y here could be any real numbers. We need to show that one of the properties of a subspace is not satisfied. And as with our previous example, there's multiple properties which fail to hold here. The easiest one to show is that this set does not contain the 0 vector. So here clearly the 0 vector in space, which would be 0, 0, 0, is not an element of this set H because the third coordinate is not equal to 1. So as soon as we see that our set does not contain the 0 vector, we know it's not a subspace of R3. Let's see how we could have also shown that this is not a subspace using some other properties. So the second property is closure under addition. So if we were to take the sum of two vectors in H, let's say x1, y1, 1, and x2, y2, 1, the sum is the vector x1 plus x2, y1 plus y2, and 2, which is not an element of H since the third coordinate for that vector is not equal to 1. So it is not closed under scalar or under vector addition. Therefore, it is not a subspace. Or we could have also used property 3 and shown that it is not closed under scalar multiplication. So here, if we were to take any scalar, let's say some constant c, and multiply by a vector in the set H, something of the form xy1, then we have the vector cx, cy, and c, which is not contained in H for any scalar c. So in particular, any scalar other than 1 would not be contained, or that product would not be contained in the set H. Therefore, it is not closed under scalar multiplication. So any one of these 3 properties failing to hold immediately means that our plane H is not a subspace of R3. So similar to what we saw in our previous example, we had seen that any line in the plane which does not pass through the origin is not a subspace, since it doesn't contain the 0 vector. So here we have an analog of that. In general, any line or plane in space that does not pass through the origin is not a subspace of R3, because it could not contain the 0 vector. All right. So in our next example, let's look at some spaces which are not quite as simple as R2 or R3. So in this next example, we're considering the set of polynomials of degree 2 or less, and we're told to let H be the set of all polynomials of the form P of t is equal to a plus t squared, where a is in R, so a is some real number. So this is the set of all polynomials which have a constant, a real constant coefficient. There is a 0 coefficient for t, and we have a coefficient of 1 for t squared. So we're supposed to see whether this set H is a subspace of P2. Let's see whether we can show that it is or is not a subspace. So here, there's 3 conditions which we can check, the first of which is whether the 0 vector is an element of this set. And in this example, we can see that clearly the 0 vector, which for the set of polynomials of degree 2 would be the function z of t, which is identically 0 for all t. And we can see that that is not an element of the set H, because the coefficient for t squared would have to equal 1 for polynomials in this set. So as soon as we see that it does not contain the 0 vector, we know that it is not a subspace of P2. Now other conditions which we could have used to show that this is not a subspace would be that it is not closed under addition. So if we were to take 2 polynomials in our set H, let's say P1 of t and P2 of t, which would have the form, let's say, a plus t squared and b plus t squared, where a and b are real numbers. The sum would be the polynomial whose constant coefficient is the sum of a and b, and the coefficient for t squared is now 2. We have 2t squared, so here the coefficient of t squared is not equal to 1, therefore this sum is not contained in the set H. So it fails the condition for closure under addition. And it also fails the condition for closure under scalar multiplication. If we were to take some scalar, let's call it c, times a polynomial p of t in that set, we would have something of the form c times a polynomial of the form a plus t squared, which would give us AC plus C times T squared, which is not contained in H for all scalars. So here, if we take any scalar C other than 1, we can see that this scalar multiple would not be contained in that set H. So since it fails any one of these three conditions, we can say that here H is not a subspace of P2. So in our last one, we're told to let H be the set of all polynomials in Pn, so those are polynomials of degree n or less, such that P of 0 is equal to 0. So that is the constant coefficient is 0. And we are asked to determine whether H is a subspace of Pn. So here let's think about how exactly this space H is defined. So here H is a set of polynomials in Pn. So in general, it would be something of the form A0 plus A1t plus A2t squared, and so on, up through an t to the nth, such that all of these coefficients are real numbers. Such that P of 0 is equal to 0. So we have one extra condition here, namely P of 0 has to equal to 0. So let's think about another way to write out this set. In order for P of 0 to equal 0, let's think about another way to describe that condition. So if we let t equal to 0 in any polynomial within that set, we see that the terms t squared, up through t to the nth, all become 0. And the only value that we're left with is our constant coefficient, a0. Now we're told that the value of that function at t equals 0 must be equal to 0. So really, another way to think about the set H is as the set of all nth degree polynomials where the constant coefficient is 0. So these would be polynomials of the form a1t plus a2t squared, and so on up through an t to the nth, where our coefficients could be any real number. So another way to think about that set here. So let's see whether this is a subspace of Pn by checking our three conditions. So condition 1 is whether the 0 vector in Pn is within this set. And clearly it is. The 0 vector, let's call it z of t, that is the 0 polynomial for Pn, would be the polynomial which is identically equal to 0 for all values of t, which would satisfy the condition to be an element of the set H. Its constant coefficient is 0. So it satisfies the first condition for a subspace. Condition 2 is that it's closed under addition. So let's say that we're taking the sum of two polynomials, P1 and P2, within this space, or this set. So we would have something of the form A1t plus A2t squared, and so on, up through a n t to the n, plus, for P2, we might have something of the form B1t plus B2t squared, and so on, up through Bn t to the nth. And the sum of those two polynomials would be the polynomial given by A1 plus B1, t to the first, plus A2 plus B2, t squared, and so on, up through an plus bn times t to the nth, which is still an element of the set H, since the constant coefficient is 0. And for our third condition, we need to show that this is closed under scalar multiplication. So for any scalar c that I take, if I multiply by a polynomial, p of t, which is in this set, I would have something of the form c times a1t plus a2t squared, and so on up through a n t n. And multiplying by this scalar, I would have the polynomial ca1 times t plus ca2 t squared, and so on up through c a n t to the nth, which is clearly still in the set H, since its constant coefficient is still 0. So since it satisfies all three conditions of a subspace, we can say that H is a subspace of P2.